Hey. All right. Happy Friday, everybody. Hopefully you have some fun plans for the weekend in addition to studying for your quiz. So just a reminder, I don't have office hours over the weekend, but please, feel free to email me or Allison if you have any questions over the weekend. And I'll have office hours again on Tuesday. I'll see you on Monday before that. So if you are in Chem 117, so you don't have lab until at least Tuesday next week, but there are a lot of things to do. So that's why I want to remind you of all of those things again. If you're in an odd numbered section, so odd numbered 117 section, you should be planning to do the nanoparticles experiment next week. You have 5 other assignments due the night before lab. Make sure you check on Canvas what those assignments are so that you get them done. All right. And then this is the announcement slide I had up while I was getting ready, while people were coming in. We have a quiz opening on Sunday, closing on Monday. It's quiz number 7 out of 10. Topics are going to be all the stuff that we talked about Wednesday and all the stuff we talk about today for the most part. So all about intermolecular forces. So intermolecular forces drive, you can talk about them between different molecules just as a definition. They drive what phase of matter your different substances are in. So we're going to talk about phase diagrams today. Intermolecular forces determine whether or not things are miscible. So a reminder, miscible means they dissolve in each other. Immiscible means they don't. So possible, impossible, miscible, immiscible. And intermolecular forces we talked about last time a little bit. They affect boiling point, and they also affect another property called vapor pressure, which we'll talk about more today. So these are all the things that might show up on that quiz. There will be 5 questions as usual, 20 minutes for that quiz, 30 points, all that good stuff. All right, so this is where we left off. We talked about intermolecular forces. So we talked about dipole intermolecular forces. We talked about ion dipole intermolecular forces. And we talked about hydrogen bonding. We talked about all those last time. At the end, last time, we started talking about this instantaneous dipole, an induced dipole. So this is just a summary of what we talked about last time. Nonpolar molecules like the oxygen molecule, O2, or the iodine molecule, I2, they don't have a permanent dipole because they are 2 atoms that have the same electronegativity, so there's no difference in electronegativity. There's no dipole in that molecule on its own. But when these molecules come in contact with other molecules, whether they're polar or not, actually, when they come in contact with other molecules, the electrons in one molecule run away from the electrons in the other molecule, basically. And we get a separation of charges, and we call this an induced dipole. These temporary dipoles form from the repelling of electron clouds. So the electron clouds repel, and we end up with temporary dipoles. And just like with our dipole-dipole bonding, the plus is always by the minus is always by the plus, so on and so forth. So that's how these molecules orient when they are nearby other molecules. So just another word, another term for this induced dipole concept is London dispersion forces, or simply dispersion forces. So we're going to call them dispersion forces for the most part because that is easier to say than induced dipole forces, or London dispersion forces. So these are the ones from the previous slide. So these involve that instantaneous dipole. So dispersion forces are important because they're found in every molecule. I'll say every molecular interaction. So if we have a sodium ion interacting with a water molecule, we talked about that last time, that was ion dipole intermolecular forces. But in that interaction, we also have dispersion forces. There are actual permanent dipoles being formed, but there is also a regular distortion of the electron cloud, which is basically the definition of dispersion forces. So if I ask you about the intermolecular forces between two molecules, they can have hydrogen bonding, and they can have dipole-dipole forces, but they always have dispersion forces too. So in addition, you always want to pick dispersion as one of the options. Okay, so dispersion versus other intermolecular forces. Dispersion is usually weaker. It's usually the weakest of the forces. So if I ever ask you what's the strongest, if there are other intermolecular forces present, it's probably not going to be dispersion. So but I say usually because that's not, not necessarily always true. So if we're comparing two different substances, if we're comparing nonpolar molecules like the ones shown on this slide, F2, Cl2, Br2, I2, if we're comparing these nonpolar molecules and their intermolecular forces, comparing that strength between the intermolecular forces of water per se, then the dispersion between these nonpolar molecules might actually be stronger than the hydrogen bonding between the water molecules. And you can kind of see that here in that iodine, its boiling point is 184 degrees Celsius, which is greater than the 100 degrees Celsius for water. So I2 has stronger intermolecular forces holding the I2 molecules together than water has of its hydrogen bonds holding it together. And that is all based on something called polarizability. So that's going to be on our next slide here. So I'm going to go back to those questions, but I want to define this since I introduced the topic. Polarizability means that we have the amount, it's basically the amount that the electron cloud can be distorted. And what does that mean? So if we have these iodine molecules and they're going to interact with each other, there are a lot of electrons in there. So iodine, if I remember correctly, is number 53. So each one of these molecules, if it has two iodine atoms, it's going to have about 106 electrons. And the more electrons we have, the more distortion we see. So it's going to say if these are going in this direction, it's going to shift these in that direction by a lot because we have 106 negatively charged things affecting 106 negatively charged things on another molecule. So it depends on the number of electrons, polarizability, and because it depends on the number of electrons, it increases with molar mass So whenever we add more electrons, we're also adding more protons and more neutrons because that's how atoms work, right? So when we add more, we're adding more mass. So if we have a higher molar mass, then we have more electrons by default. And it's related, but sometimes there is a distinction. It increases with size as well. So sometimes we can talk about things with the same molar mass that have a different size. And I'll show you examples of that on a future slide. So polarizability, if there are a lot of electrons, if we have a high molar mass, then the dispersion forces are stronger. So it's all relative, unfortunately. I can't give you a hard and fast rule about intermolecular forces. So let me write that here. So higher polarizability. Stronger dispersion forces. All right, but now, since we've talked about our different intermolecular forces, I'm going to take a little break for you guys to answer a question, okay? So we'll go back to these. So first, I'll practice with you to remember what we're talking about. So which of the following is not an intermolecular force found between HCl molecules? So raise your hand if you think that HCl molecules with other HCl molecules have dispersion forces. So do they have dispersion forces between those two molecules, two HCl molecules interacting with each other? Okay, a lot of hands, good. Can anyone tell me why? Always, everything has dispersion forces. So yes, there are dispersion forces between the HCl molecules. Every molecular interaction is dispersion forces. So that one's there. All right. What about hydrogen bonding? What do we need for hydrogen bonding? Does anyone remember? Okay, we need hydrogen. What else do we need? Oxygen, I heard. Nitrogen, fluorine. Those are our three options. So we need to have HF, HO, or HN bonds to have hydrogen bonding between our molecules. Does HCl have oxygen, fluorine, or nitrogen? No. So this one does not have hydrogen bonding. So that is our answer for this question. But let's finish up. Let's be complete here. So dipole forces. I'm going to draw my HCl molecule. Go back to our Lewis structures. So this is our HCl molecule. Our electronegativities are 3.0 and 2.1. And usually when we're talking about the difference in electronegativity, so the difference between those two numbers is 0.9, right? So if the electronegativity difference is greater than, 0.5, then it is a polar bond. And it's going to point that way. So is there anything to cancel out that polar bond? Any other polar bonds to cancel it out? No. So HCl, when another HCl molecule comes up next to it, they both have polar bonds. So they both have dipoles. So we have dipole-dipole forces. All right. So hydrogen bonding is the one that we don't have. All right, cool. That's a review of our intermolecular forces from last time and this time. So now you guys can try this. We'll spend about a minute on it. I will even draw the Lewis structure for you. You can talk to each other and, just get in your answers. There is only one correct answer, I promise. All right, let's get our answers in the next 30 seconds or so. Maybe we're just missing that many people on a Friday, but we'll see. "15 seconds. 5, 4, 3, 2, 1. Going once, twice. Okay. Beautiful. All right. So, yes, this is basically very, very similar to the previous question that I did with you guys. So, there is no hydrogen bonding in this molecule. Can anyone tell me why? There's no hydrogen. Yeah, that's why. That's one big reason why. So one way that maybe you could have gotten confused is that this molecule, if I was asking you about it interacting with a water molecule, then we could see hydrogen bonding because the water is going to contribute the OH part. So that would be if we had, a water molecule coming in here. Then we are making our, in this case, OHF sandwich. So that would be a possible hydrogen bonding, but I was only asking you about between selenium tetrafluoride molecules, not between selenium tetrafluoride molecules and water. Okay, so can anyone tell me why there is dipole-dipole bonding? Because it's polar, great. So yes, it is a polar molecule. And hopefully you were able to figure that out by my drawing. So we do have bond dipoles pointing from selenium to each fluorine. But when I drew those two bond dipoles are pointing 180 degrees away from each other. Those two cancel out. But these two do not cancel out. So we have an overall bond dipole pointing down through those fluorines. There's nothing pointing up to cancel it out. So it's all about our X and our Y directions. So our X directions do cancel out, but our Y direction does not. So it is polar, so it does have dipole-dipole forces. And everything has dispersion forces. All right. Cool. So here is an example of what I was talking about when I said that it can depend on molecular size. So molecular size is going to come from these organic molecules. So we do still have intermolecular forces in our nonpolar organic molecules, like these, what we call alkanes. So these are hydrocarbons. Another word for them is alkanes. It's just a definition, just something to remember. That's why they all end in ane. Anyway, so in these hydrocarbons, they are nonpolar because carbon's electronegativity is about 2.5 and hydrogen's electronegativity is 2.1. So that's a very small difference between those two. So we say that they are nonpolar. No matter what the geometry is, we say they're nonpolar because they're very close in electronegativity. And these hydrocarbons are differing in molar mass or molecular weight and what I call the length of the carbon chain. And this is where that molecular size comes in. So because they're nonpolar, they don't exhibit dipole-dipole forces. They don't exhibit hydrogen bonding forces, which are a category of dipole-dipole forces. They only exhibit dispersion forces. And that could be between any of the methane molecules with other methane molecules, or between any of the methane molecules with hexane molecules. It doesn't matter. They're all nonpolar, so they all only have dispersion. And when I say the length of the carbon chain, let me draw out a hexane for you, so you can see kind of what it looks like. So you might see structures drawn where it's just the lines. That's a more organic way of drawing it. I'm going to try and draw out all the hydrogens and carbons for you to make it more similar to what we've been seeing lately. So this is the length of a hexane hydrocarbon. And this is the length of a ethane hydrocarbon. As you can see, the hexane one is longer. It's the length of the carbon chain. 6 carbons in a row versus 2 carbons in a row. With the length of the chain comes a change in molecular weight. So it does still depend on molecular weight, but we see the same trend that we might expect here. As we get more atoms in our molecule, it gets heavier. And we get a longer carbon chain. Both of those things contribute to this trend that we see in the boiling point. The boiling point is increasing, which means it's harder to break apart the molecules, harder to separate them and sever those intermolecular forces. So that's what we see. We see increase in boiling point corresponds with increase in the strength of the intermolecular forces. Okay, so that's just to bring that all together with polarizability, molecular weights, boiling point, all that good stuff. Okay, so this is a little summary here, is that polarizability, intermolecular forces, and boiling points, they all increase with molecular weight. So the bigger the molecules are that are involved, the stronger the forces holding them together, and the higher the boiling point. Now we're introducing our concept of vapor pressure. Vapor pressure decreases with molecular weight / intermolecular forces / boiling point. So if you just remember the trend, increase in molecular weights equals increase in intermolecular forces generally, and increase in boiling point. Vapor pressure just does the opposite. So this is what we see in most molecules. I would say most molecules are actually nonpolar. Most molecules exhibit only dispersion forces. And this is the trend we see with that. But in more general terms, as we saw last time, intermolecular forces go up, boiling point goes up, vapor pressure goes down. This molecular weight thing only comes in with polarizability and dispersion forces. So in general, it doesn't matter what kind of forces it has. If it's got a higher boiling point, it has a lower vapor pressure. If it's got a higher boiling point, it's got stronger intermolecular forces and a lower vapor pressure. So we see that over here with our boiling point versus vapor pressure. Boiling point is increasing as we go down the table. Vapor pressure is decreasing as we go down the table. And this is in Tor. All right. So now, just to try and clear everything up that we've talked about so far, nonpolar versus polar, if the same size, then polar IMFs, like dipole-dipole forces, are greater than dispersion. So anytime we're talking about two of the same molecule, for example, if we're talking about two of the same molecule, and I ask you, what is the strongest intermolecular force? If they are polar, the answer should be dipole-dipole forces, not dispersion, even though they all have dispersion. It's only when we're comparing different molecules that we have to worry about the size. So if we're talking about, if we take a look at this table, if we're talking about nitrogen and carbon monoxide, they have the same molar mass, and they have the same molar mass, and they have a very, similar boiling point, but that changes as we go down the periodic table. So as we go down the periodic table, we see a bigger difference. So there's a bigger difference between bromine and ICl. So bromine has a molar mass of 160. ICl has a molar mass of 162. ICl is polar, so it has the higher boiling point. It has stronger intermolecular forces. And that's between two ICl molecules versus between two bromine molecules. So the first thing you want to do when you're comparing the intermolecular forces between two sets of molecules is see if they are comparable in size. If they're comparable in size, dipole-dipole is stronger than dispersion. If they are not comparable in size, then the size effects usually matter more. So higher molecular weight equals stronger IMFs. So you want to compare those two things. You want to check on their size first, and then you want to see if they are similar in size, polar is better than nonpolar. If they're different in size, then the higher molecular weight is going to give you stronger intermolecular forces. And I'm going to make it pretty clear for you. I'll give you, pretty differently sized molecules if I ever ask you something like that. I'll make it pretty clear. Don't worry. All right. So then just wrapping up our intermolecular forces, hydrogen bonding is found in our water molecules, and it's responsible for, as we saw, it's responsible for a lot of the properties of water. It's high boiling point compared to similar molecules. And it's responsible for things like surface tension, which is kind of what holds this snowflake together. And that's what lets us, have boats on water. In addition to, those little bugs that kind of run across the water. High surface tension, high boiling points, low vapor pressure. Basically everything that makes water water is based on hydrogen bonding. All right, and then we talked about isomers a little bit back in when we were talking about polarity. Different isomers can have different IMFs because they can be polar or nonpolar, or now that we've learned there's also a different type of dipole force, they can have hydrogen bonds versus not. So these have the same formula, but different boiling points because of hydrogen bonding. All right, so that's our summary of intermolecular forces and how it relates to, different properties of things. We're going to go into a little more detail with vapor pressure and with phase changes here. But this is our summary table of the definitions of the interactions, examples of the interactions, and their strength when we're talking about molecules of comparable size. And that's about, within, say, 30 grams per mole or so. Okay. So that's just a summary table for your reference to help you with homework and stuff. So now just a little bit more on vapor pressure. So vapor pressure is defined as the pressure of the gas above a liquid. So we've talked about the phases as very separate things. We've talked about reactions as very separate things, but we're going to talk at the end of the semester about equilibrium. A liquid and a gas are always actually at equilibrium in some container. So the liquid and the gas have a little bit of equilibrium. Some of the molecules are liquid state, some of the molecules are gas state, and it depends on intermolecular forces. And this picture is just showing us the kinetic energy needed to escape. And when we say escape, we mean change from liquid to gas. So it's escaping from the liquid phase. It needs more kinetic energy. It needs a higher temperature generally to change from a liquid to a gas. That's all that this picture is showing. And boiling point is defined as when the vapor pressure is equal to atmospheric pressure. So when these two pressures are equal, we will have boiling. That is when more of our liquid molecules will start to escape into the gas phase. So you have to increase the vapor pressure of the liquid to get it to be equal to the pressure of the atmosphere for boiling to happen. And we increase pressure generally by increasing temperature. So this is a picture of vapor pressure versus temperature. So as temperature goes up, they're not straight lines because we are not talking about gases. These are liquids. So gases, it would be a nice straight line as we saw in the lab because they're directly related. But vapor pressure, when it comes to liquids, is not a direct relationship. So it's not a straight line, but it is always increasing with temperature. So higher temperatures give you higher vapor pressures. And this line up here, our 760 torr, 760 torr is 1 atmosphere. 1 atmosphere is our general pressure at sea level. So this is the boiling point, what we call the normal boiling point of these 3 liquids. So as you can see, some of them have lower boiling points than the others. So water has the highest out of the 3, that are on the main graph. Ethylene glycol is way down below. We're not going to talk about that one for now. That one has very, very high boiling point, meaning it has very, very high intermolecular forces. But the main takeaway from this graph is that if you take a look at any particular vapor pressure, like if you looked at vapor pressure 400 torr, then you would still see the same trend. You would still see that diethyl ether has a lower temperature than ethyl alcohol or water. So you just want to learn how to read these graphs. You will see some of them on your homework. So on that note, let's take a quick clicker question. And I'm going to label them for you. Oops, sorry. Give me 1 second. A, B, and C. So which substance has the highest boiling point at 400 torr? So if we were to somehow lower the atmospheric pressure to 400 torr so that we would have boiling happen there, which one would have the highest boiling points? Diethyl ether, ethyl alcohol, or water? Which one has the highest temperature where boiling would happen? We'll spend about a minute on this. This is all just about reading this graph. Boiling point is a temperature. We're looking for a highest temperature at 400 torr. I'll give you another 30 seconds to get your answers in. We have a little bit more to get through today. All right, 10 more seconds. There's 3 choices. It got a little cut off. It's A, B, or C. You got a 33% chance of getting it right if you guess. 5, 4, 3, 2, 1. Going once, twice, sold. All right, great. Yes. So it's got the same trend as which one would have the highest boiling point at atmospheric pressure. So we saw those boiling points at 760. We have the same trend. If we could somehow lower atmospheric pressure to 400 torr, we would see the same trend. Water would have the highest boiling point of these 3. And it's based on intermolecular forces. So highest boiling point is strongest intermolecular forces. And if we're looking at them all at the same temperature, I'll go back to the previous slide to do that. Let's see if I can. So if we're looking at them all at the same temperature, say here, that's the best place where we can see them all at the same temperature. The one with the lowest vapor pressure at the same temperature is the one with the strongest intermolecular forces. So that's still water. All right, so if I ask you about vapor pressure or boiling points, you can always go back to what you know about intermolecular forces to answer the question. It's all based on intermolecular forces. All right, and then if anybody has ever, used a cake mix, the cake mix usually tells you that you need to use different temperatures on your oven when you are baking in high altitude areas, and that is based on pressure. So how do the boiling points of liquids at high altitudes compare to those at lower altitudes? So high altitudes, I'll tell you, high altitudes means it's a lower pressure. The further away from the earth you get, the surface of the earth you get, the lower the pressure. So if we're comparing the boiling points of diethyl ether, for example, at sea level versus the boiling point of diethyl ether at some other altitude with a lower pressure, the boiling point is going to be lower. All right, anyway, that's just a fun relationship to things you might know from baking a cake. All right, our last thing for today, we're not going to get to chapter 9, but that's okay. Our last thing for today is phase diagrams. So the normal melting and boiling points are at 1 atmosphere. So 1 atmosphere is our sea level pressure. That's what we call normal melting points and boiling points. So what do we know what can we see from this phase diagram? So this phase diagram, you guys are going to have to, analyze a bunch of these, but this phase diagram shows us that solid is the one that is usually in, the furthest left on our phase diagram, then liquids, then gases. And that comes from this temperature idea. So if you think about something that like water, at really, really low temperatures, water is ice, it's a solid. In the middle, it's a liquid. And then if you heat it up, it boils and it's a gas. It works the same way for pretty much every substance. Solid is going to be the furthest to the left on our picture. Liquid is going to be in the middle. Gas is going to be on the right. So I would take a look at maybe this top part if you're ever not sure when you're trying to label it. So further up, higher pressure, we're going to see something similar for most things. Okay. So that's how you label those. Solids, another way to think about it is solids are usually what we see at lower pressures. So lower pressures and lower temperatures, because we're squishing those molecules together really densely, making a solid. Anyway, those are the phases that you want to recognize on, the phase diagram. Solid, liquid, gas. They're all going to be in the same relative position on any phase diagram you draw. And then our transitions between the phases are represented as these lines. So the phases are the regions. The phase changes are the lines. So the melting and the freezing point, it's going to be the same thing. We're either going to liquid or to solid, depending on whether it's melting or freezing. That's going to be the line in between liquid and solid. Vaporization, making a gas, boiling, that's going to be going from a liquid to a gas. The opposite is condensation, going from a gas to a liquid. So that's what we see on this line between liquid and gas. Then the more rare version is sublimation versus deposition. So sublimation is when we go from a solid to a gas. So that's, if you've heard of sublimation before, you've heard of it in terms of carbon dioxide. So dry ice is solid carbon dioxide and it sublimes at room temperature. It sublimes into a gas. So sublimation is when we go straight from solid to gas. Deposition is the opposite. So that might be the first time you've heard the word deposition, but deposition is the opposite, going from a gas to a solid. And our normal boiling points and melting points are where they cross 1 atmosphere. Okay, so one thing that you'll notice from this that you might not have known before is that melting points and boiling points, they depend on pressure. So the temperature that you melt something is not always the same. It depends on pressure. The temperature that you boil something is not always the same. It depends on pressure. So there's a few other points to notice on here. This is called the critical point. Above that point, above that temperature and pressure, weird things happen. We call those supercritical fluids. And this one is called the triple point. The triple point is where all 3 phases exist at the same time: solid, liquid, and gas. And you guys can check out this video. This is a video of the triple point of water, where you'll see both, or all 3, solid, liquid, and gas water at one time. It's pretty cool. So this is a phase diagram for carbon dioxide. It looks a lot like the one we saw on the previous slide. And you can see this sublimation that happens at 1 atmosphere. So at normal atmospheric pressure, at like sea level,
we see sublimation of carbon dioxide. We don't see liquid carbon dioxide. If we go up to really, really high pressures, then we can see liquid carbon dioxide. So it does exist. You just need a high pressure to achieve it. And the phase diagram for water, is a little weird. So I want you to note the slope of this line. So the solid liquid transition for water is different than for carbon dioxide. And that's because liquid water actually has a higher density than solid water. And you've probably seen that because ice cubes float in your drink. So liquid water has a higher density than solid water. So when we start to push the molecules together at higher pressures, so increasing the pressure means we're pushing them together. If we go like along this 0 temperature line, we will actually turn into a solid before we turn into a liquid. So there, along that line, we're increasing the pressure and we actually change from a solid to a liquid as opposed to what usually happens. What usually happens is if we increase the pressure at any certain point, it goes from liquid to solid. But water is the other way around. Water at some temperatures, if you go from lower pressures to higher pressures, you end up with solid to liquid. Okay, so that's what you take away from these phase diagrams. And we can, see that on other phase diagrams as well, ones that are not labeled, ones that are for compounds that we don't know. And I have a few examples in here, so please take a look at these examples. So I have some more definitions about carbon dioxide and water phase diagrams. And I have an example of an unknown substance. So check out this example so that you can learn more about phase diagrams. Next time we will talk about energy. Have a good weekend, everybody. Don't forget there's a quiz opening on Sunday. Make sure you study for it.